This is a production of Cornell University.
All right, thank you very much. Bonjour tout le monde, c'est mon plaisir de vous accueillir aujourd'hui pour le premier séminaire officiel de la session. Anthony, I don't think it works. Javier, got it, yeah? All right, thank you very much, Vipan. So yeah, Louis Longchamps, Digital Ag assistant professor of digital agronomy. So I want to tell you a little bit more. So last week it was like a very quick lightning talk about a few things that we are doing in the program. This week I would like to go a little bit more in depth in what we're trying to achieve, bringing the people together, trying to change things maybe in different ways, how we want to accelerate change in agriculture so that we can reach sustainable ag and agroecology faster than the pace that we are on right now. So I'm sorry that I want to share something early on with you here. Always the same thing here. You need to click on the thing first. Yeah, I want to share this with you. This is I watched a TED talk from Rockstrom, Johan Rockstrom. It came out like 3 weeks back. And in the TED talk, he's presenting, so it's kind of an update on the planetary boundaries that came out like in 2009, but there's a new report, 2023, and he's talking about the tipping point. So here what you see is that you see a human pushing the earth and potentially crossing that tipping point, and then the new normal is hothouse herd. So this is kind of a scary thing. But then he goes in detail and then he shows those tipping points across the planet. And we can see that on, we can see that for a bunch of those, like the 5 first ones, we're already in the line where we can see those tipping points changing how our planet looks like. Okay, so this tells us that I said that we need to have something happening, not in 10 years, not in 20 years, but right now. We need to see change. And then Sustainable Development Goals from the UN started in 2015. We are in 2024. The goal is to achieve all of that by 2030. Clock is ticking. So we make a lot of innovations and progress in ag research. Okay, we have different fields, and we are kind of attacking the problems from all sides, and we are finding solutions. And we all hope that it goes like this. So we invent a solution, we run with that thing, pass it to the farmers. Farmers take that thing and then just run with it, and then change is happening. But the reality is that it's a little bit more complex. Once you have invented something, once you have put something together that you've demonstrated with scientifically that it can have a change, it can make a change. It's not necessarily happening at the pace that we would like. Okay, so this is an illustration here of a recent paper based on remote sensing. They looked at cover crop in the Midwest. So how much do you think, what was the percentage in 2011 of the land in the Midwest that had cover crops? Okay, spoiler, 5.4. And now you look at this, we really want that thing to work. It doesn't work. It works. Again, you look at the title of the paper, Rapid Increase in Cover Crop Adoption Across the Midwest. What rapid increase looks like is like this. Yeah, this is real data. I mean, we have plenty of scientific evidence that cover crops are good and they are compatible with farming, yet adoption is tricky. Other examples, this is in the Deux-Sèvres region in France. I'm just going to read that thing. So a project involving 400 farms and around 40 villages in the Deux-Sèvres region in western France, where scientists are experimenting with different techniques to cut pollution. Even the farmers who participated in the experiment and saw the results with their own eyes did not noticeably change their practices. What does that tell us is that you had scientists there demonstrating and experimenting on farmers' field, but farmers were not the leaders of that thing. They were observing it going, and it did not stick. They did not adopt it as their own practice. They did not integrate it in their practices. Another long quote from Dan Towery, conservation practitioner in Indiana. Okay, if no-till corn is done, let me turn around. If no-till corn is done incorrectly, for example, if a farmer uses the wrong planter setup or does not use starter fertilizer on the planter, corn yields and profits may be reduced. If this happens when a producer first switches to no-till, they may be more likely to go back to previous methods, in this case, tillage. There is always a learning curve with something new. This makes some producers risk-averse because if they do something different, they may miss important details and run the risk of reduced yield. This is kind of a simple thing that we can all picture in our head, but this is an important process going on. When farmers try something to gather evidence that it works for them, if it doesn't work, then now they have evidence that it doesn't work for them. Okay? So what I want to get at is that change is a people's process. A very interesting paper. They are about to release it, but I was able to get access to it because I know the authors from Ruiz and Dumont, 2024. What they did is that they studied 50 farmers over 6 years that were adopting cover crops. Okay, like the process of adopting the practice of cover crops on their farm. What they did is, so they are social scientists, and what they did is that they tried to see where they are in that chain of process from inaction, where you don't even have an opinion, you don't really care, to integration. Okay, and integration here, it's a little bit different from adoption in their perspective, where if you do something on your farm, it's considered adopted, like you can check the box, they adopted it. But in their definition, it's more like a tractor. If your tractor breaks, you're not like, I'm not gonna use tractors anymore, doesn't work for me. You're gonna fix the damn thing and make it work because it's integrated in your operations. It's part of your farming. Okay. So from inaction to integration, sorry. Then there are 3 steps here, from resistance to inflection. And all my life, this is where my scientific work, this is where I have operated. I'm studying things in the field, research farm, even on farms, gathering evidence, analyzing the data, preparing scientific publication, extension publications, presentations like that, seminars, and then I show the evidence that things are working, will benefit the farmers, things will make a better life, better everything. And then the idea here is to tip the perception from, yeah, it doesn't work, it's not good, to, oh yeah, okay, yeah, seems good, let me try it. So it's just like to change, to go from negative to positive. But I kind of have stopped there normally. Once I publish stuff, then I move on to the next thing and then continue working on things that are not finished, and then working on other stuff. And then I'm just trying to push that information. Yeah, it's going to work. You should try it on your farm. But this is similar to a lot of scientists where we stop here. And then at that point, farmers need to take that baton that we are giving it to them. Now they need to pick it up. When they perceive a positive benefits on it. So at this point, what they will do is that they will experiment with that new approach, new technique. In my case, it was precision management, input management, but it could really be anything. They want to obtain evidence that it works for them. We ran a series of interviews in New York to ask farmers how are they experimenting. Let's say we met with 15 farmers, 2 hours each, and then we just discussed the experimentation process. And you would be surprised, and a bunch of them, they would do a side-by-side experiment And then I'm asking them, I'm digital ag. So I'm like, okay, what data do you get? How do you analyze their data? And more than one answered something like this. I see it from the tractor cabin when I harvest. Yeah, it worked or it didn't work. That's the data that they use to see, to move on for next year, that will influence the decisions for next year. This experimentation process is not trivial, okay? I put it here because I wanted to show that we went from the Teosinte to the corn that we know. There was no experimental design, there was no science involved, it was all on-farm experimentation. Same thing here for the Three Sisters way to grow crops, or for the use a fish head to bury under each crop to get the nutrients. No science, no experimental design, no statistics or nothing involved. And this kind of have evolved towards things that work, things that are very significant, like from Teosinte to corn. I mean, this is something. Okay, so I just wanted to point this here, that this is an important process happening in parallel with scientific research that we are doing. Okay, so when farmers are experimenting on their farm with that new practice that they were convinced that, whoa, it could do something for me, help me more environmentally friendly, or improve my profits and things like that. When they experiment with it, and if they see something that doesn't work, then the danger is that they are back to square one, because the square one is resistance. I know that it doesn't work, so now you have all that work to go back to before they can try again. And in this study, they looked at how long it would take for farmers to go from one box to the other, and it takes about 2 years on average. Okay, so this is a real setback. And thinking that we need to accelerate progress, I mean, this is not trivial. So I perceive this experimentation here as a crucial process for change and progress. Okay, so then what we realize is that everything that we develop in science will go through the filter of on-farm experimentation before it creates a real impact on agriculture. And what we know is that conventional research benefits from all the bells and whistles of technology, sensing, data organization, data analysis, and all that, while on-farm experimentation is a very low-tech process, which means that it's prone to error. Because if all you have is to look by the tractor window, you may either make the wrong decision, or you may not understand why you made the wrong or the good decision. Okay? So the premise of my program is that digital ag can support endogenous experimentation. And this is not just my program that does that. A lot of people that have developed precision agriculture techniques really realize that, yeah, if I'm doing this, if I'm able to gather all those yield maps, those as-applied maps, and all the good stuff that is going on in precision ag realm, maybe we can use it to experiment. And then there's a bunch of different groups across so you see groups from Canada, NGO, universities. You see a group in France here. And this is really a very short, partial list, but it shows that like people are trying to make this like a new way of collaborating with farmers through the data. Okay, so we see a diversity in approaches from groups that are more researcher-centric. So they would build a protocol and try to disseminate it to as many farms as possible, to groups that are more farmer-centric, strict experimental design versus more open design. So here you have a protocol that everybody needs to adopt to be part of the network, while here everybody can do their own protocol. And then you have here more researcher-centric, where you want to have more, the goal is to do scientific publications. And here you have more farmer-centric. The goal here is to have more pragmatic information to see what works for them on their farm. Okay, so this is cooked up like just through those points there to illustrate a little bit the distribution. But what's interesting is that all those groups have common challenges: how to gather and contextualize the observations, how to analyze the data, how to help farmers learn from their experiments. And now that we are starting to engage with farmers, those challenges emerge, and then we need to develop the science, the solutions to make this process more fluid and more easy so that we can scale. In this process, basically what we are doing is that we're changing what we used to call an anecdote. Okay, if you have a farmer, you go visit with a farmer, hey, I've seen this in that field. For scientists, we see this as, okay, this is an interesting observation, and actually we use observations like that to create hypotheses. But for us, this is an anecdote. It's anecdotal. We don't necessarily consider this as potentially a scientific observation. But with data science, what we can do is that we can transform this into something scientific. Everybody have heard of the G by E by M. So the idea here is to say, okay, you saw that observation. What was the G by E by M context of this observation? And now this makes that one observation worthy of a scientific database that we can use to start learning, to see trends and patterns that can emerge that we may not have seen with the traditional small plot experiment, or by just talking with farmers at the coffee shop and learning from their anecdotes here and there. Okay. Globally, if farmers' innovations were valued at just 0.5% of farming production, which is $4 trillion, that would match formal R&D investment from the private sector, which is about $20 billion. So I put it there just to show like the scale of, if we are able to transform those observations into scientific data, I mean, all of a sudden we have access to a wealth of new data to learn about agronomy and about agriculture. So here it's not just about data. Okay, so I want to kind of describe a little bit what is the on-farm experimentation cycle. So here first, we need to engage with farmers. Farmers need to understand what we're trying to do, why we're doing it, and we need to understand why also they want to experiment, and to be on the same page with them, so that when we engage, we help them reach their goals. And then comes the part where we acquire the data, we clean and assemble the data, organize it, we do some first analysis, then we continue the analysis with some things that are more in depth, and then we discuss with the farmers and partners to learn together from the results. And then we have a process to review and repeat. And the idea here is that if we are able to close that loop of experimentation within 1 year, we are more in line with what farmers typically do, that they iterate until they have a working solution, as opposed to how scientists experiment, where we want to replicate 2-3 years, the same experimental design, the same protocol, so that we can publish from it. Okay? But if you look at this thing here, you have really different groups going on. So here you will have more agronomists and social scientists. Here you will have agronomists, but also data scientists involved. And again, here to interpret the results and to understand the farmers and to help farmers learn from that result, again, we have agronomy and social science. So this makes it a co-creation process where we recognize local actors' capacity to explore, and we build on the scientists' capacity to quantify and detect patterns. Okay, this is at least in digital agronomy, this is what we are good at, to quantify things and detect trends and patterns. So this is really a good example of decentralized research, and the idea is to try to be iterative and flexible. So what I wanted to show you here is this is a transdisciplinary approach, okay? Because you have all three, agronomy, data science, and social science, working together. Agronomy is there for consistent interpretation. Okay, so we use the science soil and crop science, chemistry, physics, biology, to have consistent interpretation. We use that science to interpret what we are seeing. Then we use data science to get greater certainty. So whatever we conclude, whatever we analyze is based on actual data. And then we have social science to make this a more effective process to help people work together, basically. So at the middle of this is the on-farm experimentation process. So that was kind of that was my intro on farm experimentation for you to understand a little bit what is the principle. And what I want to do next is to show you a quick example of how it could look like in practice. Okay, so I've never done a program like this. When I was at Agriculture Agri-Food Canada, I started to work on a living lab with farmers. The objective was to reduce the pollution in the Saint-Pierre Lake, which is a part of the St. Lawrence River. And that was the only thing. And then we just start sitting together and trying to understand who is doing what. Scientists like explaining better what is the problem, farmers trying to understand the problem and maybe link to some practices. And then I left and I came here. So that would have been my first experience here. My first experience here was with biologicals. So what I did is that I thought, okay, I want to try this idea, the idea of really helping farmers experiment, but on their terms, to support farmer-led experimentation. So what I did is that I consulted with extension specialists and industry service providers to learn like what are farmers interested in this year, what are they experimenting with, and a lot of this came back on biologicals. Okay, and the idea was that so biological is like it's a bacteria or a cocktail of bacteria that you apply with the corn at seeding, and this thing is able to fix nitrogen and supply a part of the nitrogen to the crop. And on that, the beginning of the project, everybody wanted to experiment with it first because it was a big promotion campaign from the company, but also the numbers were kind of aligning. Okay, they were saying that that would provide 40 units of nitrogen, so that would look like a $5 saving per acre for the farmers. So they kind of said, okay, let me try it. Basically, they went on the tipping point. They were convinced to try it on their farm. So then we consulted with specialists in soil. So this is a soil microbiology project. So I'm not a soil microbiologist. So the process of on-farm experimentation relies on working with experts. So here we consulted with Dan and Alicia to understand, like, okay, how is this thing working? So basically, the bacteria, what happens is that you have the bacteria Klebsiella varicola in the soil, in natural, it's there naturally, okay? And then it fixes nitrogen, being like in symbiosis with the roots. And then when it has enough nitrogen for its organism, boom, it stops fixing the nitrogen. Okay, so what the company did is that, okay, that's a bacteria that is very good to colonize the corn roots. So let's modify it to make it better at fixing nitrogen. So they looked at the genome, and then they found the part where it says, okay, I had enough nitrogen, and they just removed that part. Okay, so that's what I learned from working with soil microbiologists. And then with this, they were able to with this, then the process would restart indefinitely and then just continue fixing nitrogen nonstop, and that's the nitrogen that becomes available for the crop. Okay, so once talk with the cooperative extension people and service providers to learn, okay, what people are experimenting. Then I consulted with specialists to learn a little bit more about the topic. And then after that, we met with farmers to understand, and with the specialists in nitrogen and corn and soil, to just generate some questions. What are the questions that will be relevant to understand with this process? Okay, and the questions that came out are, okay, what is the effect on crop nitrogen status? We're not just looking at yield. Of course, we will look at yield, but not just the yield. We want to see, does that increase the nitrogen status of the crop? will the organism be present in the soil during the season? If it's not there, that means it's not doing anything. And farmers wanted to know, is there a link with some management that I'm doing, with the type of soil, with the weather, if it's a dry year or a wet year? Okay, so with all that and learning from the soil microbiologists on how to collect, transport, and store and process the samples, then we just went and collected a bunch of samples. So we met the farmers via the CCE and the cooperative, Cornell Cooperative Extension, and the service providers to have some address, some names, some phone numbers. So we contacted them. And then those farmers explained to us, okay, what is my experimental design? Where is the field? They met with us in the field. There's a flag there from here to there, you see. So that was a little bit of a cumbersome process, to be honest. But we were able to see where their experimentations were taking place. And if you look at this here, it's a little bit all over the place. So you see normal strip trial, alternative strips, side by side. So this is very common how farmers experiment, just side by side like this. Adjacent fields, so they kind of assume that those fields are very comparable, so they would test this. We even saw that one, edge rows. We know very well about the edge effect, but still some farmers, I mean, he said like, yeah, I don't care much about the side, so I'm gonna put the control there. We didn't say like, okay, then we don't engage. We said, okay, let's collect all the data still, and when it's time to analyze it, it will become a confounding factor, and then the farmer will learn from this experience rather than if we just tell them like, no, that doesn't work. Okay. Okay, so then we went there, and with interns, students, we collected a bunch of samples at every location, trying to make it like very efficient trips every time we went out. Then Phil worked on a process to simplify retrieving all sorts of public domain information, such as like the weather data, remote sensing imagery, drought index, topography, and then soil series. Okay, so just by delineating the boundaries of the field, then all the data is aggregated. So now we have this to contextualize those observations. And then this part was tricky. We went and consulted with the farmers to know like, what did you do in this field? All the step from planting to harvest and cover crops, and we had all sorts of things there, and we had to do a lot of back and forth to get that information as accurate as possible. But it was all on paper, and it was a little bit tricky. And then we processed those samples, the soil root samples, to detect the presence of the bacteria using qPCR. Okay, so now we have like a mountain of data, okay, from all the context data, all those agronomic sample data, all the data that came from filling out those fields. So this is digital agronomy right there. I mean, it's just like a pile of data. So we wanted to say, okay, how do we present this to the farmers so that they learn something? I mean, at that point, it felt more like, man, we're going to confuse them more than anything else. So what we thought is like, okay, let's transform every data into something that looks more like an infographic, and that can be, that is more like a graphic that can be analyzed briefly and simply. Okay, so each data, we generated infographics. So I'm not going to go too much in depth on this. But for each piece of data, we had something like that. So here, I mean, it's not so easy, but you have the treatment versus the control, and then we would be able to do like distribution curve. Okay, so like fairly simple. The yield coming from the treatment, the yield coming from the control. Are they perfectly overlapping? Is there a shift? Is there a difference? Okay. Then here, that data here is a little bit trickier to understand, but this is the nitrogen versus the yield potential. And what it shows is that here you are in the response part of the curve. So more nitrogen equals more yield. And here you are in the flat part. So more nitrogen doesn't change anything. So what we wanted farmers to see like, hey, if you're here and you put 40 units less, more or less, it's not going to change your yield. Okay, so that was an important piece of information. Then after that, trying to see like, okay, how can we illustrate the qPCR results? So we draw like really where and how we collected the sample, and then we did an infographic with this so that they can quickly see, is there a bar or there's nothing there? I don't see any data from that. Then after that, remote sensing helps us like see like is there spatial variability in the field, and then the weather data showing like it's maybe a little bit easier to see here, but them versus the rest of the group, and then you can start seeing, okay, was there drought during that year? Was it a dry year, or it was a normal year, or then you can start seeing it. Then another piece of information that we wanted to add was benchmarking. How did your field? So you will find something in terms of your yield, presence of the bacteria, and your nitrogen status. But how is this when you get this information, how did your management compare to the other people in the network? Okay, we had 23 farms, so we were able to draw box plots like that kind of illustrate the entire group. And with this, we can put, okay, this is your farm, so you can see, okay, here I had quite low growing degree days. My wheat pressure was a little bit high. I had one of the highest yield in the group. You see, so now you quickly see by benchmarking with others, like how things are panning for you, where you stand. Okay, so now that we had like, okay, those infographic, we did not just throw those at them by themselves. We provided a key to help them interpret the results. Okay, so that they would go through that key, flip through the pages, and then see, okay, this is how I interpret this this result. And with this, they would be able to get to a conclusion for each of their sites. Okay, remember that it is side by side. You don't have replications. It's 1 year. Okay, so you have really one thing to look at, and from this you want to conclude something. Of course, it's not going to be a scientific conclusion, but what we're trying to do is to stack layers of evidence that kind of all point in the same direction. If you have 10 things pointing in the same directions, conclusions are stronger. If everything is all over the place, conclusions are weaker. Okay, that kind of approach. That's what the data allows you to do. So okay, so we went through the yield first. That was the most important question for them. Then nutrition index, and then was the bacteria in the field or not. And for each of those, they would mark if it was very clear or it was fuzzy in their interpretation, just to allow them to, yeah, decide something. Because if you have to be perfectly clear, it's better to have a conclusion with a level of certainty than nothing at all. Okay. And then with this, we would generate a conclusion and a level of confidence. So it looked a little bit, the results were a little bit all over the place, but here what I wanted to show is that in general, there's a good agreement between very simple, just looking at yield and adding more data. But what it does here is that when you see something like, hey, it didn't work for me, if you have more data, what it allows you to do is that you can learn why, allows you to ask questions why it maybe didn't work. Because if you just have it didn't work for me, then you may just ditch it and never return again. But if you're trying something new, if you understand why it didn't work, now you're kind of willing to give it another go, maybe the following year, or to kind of pursue the learning process. Okay, and then that allows us to kind of see at the network level to understand a little bit more what's going on. And I'm going to go briefly over this here. So Phil used AI to try to understand a little bit what's going on in the data. Okay, so we looked at at the presence of the bacteria KV, and then we just threw like all the variables, try to see what could explain the presence, absence, or the level basically. And then we saw like, okay, it's inversely related with the other bacteria. So there are two bacteria in that cocktail. And if one bacteria picks up, then the other one is kind of recessed, and vice versa. So that was kind of interesting, and that would explain why they put two. But then there was a bunch of things that some make sense, organic matter, some are maybe a little bit harder to interpret. But then what this does is that it could be, so some of those it's easy to dismiss. Yeah, it doesn't, like giving an agronomic diagnosis of that kind of data, you can see, yeah, no, that doesn't make sense. And working with farmers also, they can quickly see things that make or don't make sense. But what it does is that things that we don't have a clear answer, why is this so impactful? Then it could generate new hypotheses for research. Is there something about the slope, something about the calcium that could change something in the abundance of the bacteria in the soil? So, I mean, if we had a conversation with specialists, we could dismiss some of those, but some of those things coming up, we could investigate further. So I wanted to touch on this because this process here is kind of powerful for problem finding, for generating new hypotheses. Instead of generating your research hypothesis based on a farmer that points at something that they saw in their field, that's kind of interesting. But now we have a new process that says like, hey, this is happening. We see that consistently over the years, over the fields. We don't understand why there's such a strong relation here. Oh, now that's a new kind of interesting research project to start. Okay, so we wanted to learn from that first iteration of on-farm experimentation. So yeah, we learned that farmers appreciate this way of collaborating and were engaged. Basically, they were doing it either if we were there or not. Okay, the engagement was really to exchange the data and then work together to interpret the results. Data exchange was a mess. Okay, the flow. This is a very slow flow. That was not easy. And the conclusions with data are what we see is that they are more nuanced and they raise questions. So ideally, it would be very clear for farmers what they learn from their experimentation. But the reality is that when you do a side by side, you cannot have the same level of certainty that when you do a scientific experimentation. But yet you can learn something. Okay, so this kind of fueled the second wave of development. If we are going to do another cycle of on-farm experimentation, let's be more prepared to make it a little bit more easy, because by the time we started the first project and the time that we had all the results ready, it took 2 years because it was such a mess to go through, and it was like a learning process. The idea here is that we need to be nimble, being able to kind of make it happen quick so that we can do a full cycle in 1 year. So let's try to develop tools that will help us do that. One of those tools to quickly learn and to maybe allow for a little bit more diversity on what and how farmers want to learn is the experimentation card, the experiment card. We're basically asking, okay, what is your hypothesis? How are you going to test your hypothesis? What are you going to measure? And how are you going to interpret those measurements? Okay? It could be very simple, but at least it kind of puts on paper a little bit of more motivated or more practical way to experiment for them. It helps them like crystallize this on paper. Then we are working on the development of a OFE dashboard, and this will allow us to better capture the data. So we want to build a web tool that will allow farmers to say like, okay, I'm dedicated to experiment in that one plot. They would not do this for their entire farm, but I'm experimenting in that one plot. I have scientists from Cornell, from different groups coming and helping me to extract the information and learn more from that thing. So our hope is that they will be willing to spend a little bit of time at night to kind of populate and explain what they did in the form of a timeline. Okay, so they would just add every operation that they did during the season for that one field. And then with this, we will have access directly to all the detailed information. Then we are starting a survey on farm experimentation and digitalization. So we want to learn a little bit more. There's one survey that exists, and it said that 90% of farmers were experimenting. But now we want to see, okay, does that hold for New York? And then learn a little bit more about that process, like what kind of data they collect and how they interpret it. So yeah, so Katie, Allison, and Myrtille will be collaborating in this project. So this is great. And then we have a new website coming up, Farmers Data Lab, where we want to kind of centralize both the information about what is this process, but also a way to get engaged and for farmers to work with us. Just wanted to touch here that the next round of on-farm experimentation next summer will be on adjusting nitrogen rates in corn after cover crops. So this project was funded by the New York Corn and Soybean Grower Associations and in collaboration with the American Farmland Trust. So that's nice, because when we presented the project, I presented it this way, like we want to help farmers de-risk their experimentation and learn more from it. And the Growers Association, I mean, they liked the idea and they funded it. So that was kind of a good, that was a positive thing for the program. Okay, so now I just want to finish or to conclude on how I see that this could become like a little bit of a vision for the future if we are able to scale this process. Okay, so we have farmers here that are after pragmatic knowledge. They want to find things that work. They don't necessarily understand why. The same thing as when they developed the Three Sisters, they may not have understood exactly how the beans were fixing nitrogen. It was just pragmatic. It works for them. Okay, this is what farmers are looking for. Then we have academic research where we're looking for semantic knowledge, something that is general knowledge that can be universal. Okay? That's what we're looking for. In this part here, we have observational research. So it's all anecdotes that are transformed into scientific piece of observation that can be used in the database for analysis. And this way we can find trends and patterns in the data generated here. While here, we are developing the experimental design so that we can run statistics and quantify the processes and explain like causality and better understand. So the idea here would be that those two would work together. Both are very important for the acceleration and the transition to a sustainable ag. And how it could work is that with this here, we could generate hypotheses, as I was saying. Okay, maybe sometimes we see something that is very strong, but we don't understand why. So that becomes an hypothesis for research. I want to say here also is that if we just spin that wheel without the connection here, maybe we will find something that works. But if we don't understand it, maybe over time, like in 20 years, 30 years, boom, the thing will break. And then we don't understand why, because we did not have a clear understanding of the processes behind. That's why the connection is super important. But then here, academic research provides an understanding so that, yeah, we can roll with that pragmatic knowledge and really continue the progress and accelerate the progress. And in this way, back to my title, that's why I think farmers will lead the transition, because when in this process, farmers are leading the experimentation, the exploration process. Okay, so people that are making this possible, I mean, I did not realize before putting that slide together that so many people were involved. This is awesome. So grad students, Alex, Phil, Katie, and then all the interns that were with us over the years. I mean, during the season, I mean, when we are going to on all those fields, that having a big team allows us to just like hop from one field to the other and be very efficient. And then collaborators to the program and funding here with Cornell AES, USDA, Atkinson, CIDA, New York Growers and Soybean Association. Okay, so if you want to learn more, and I'm going to stop on this, there's an important paper that was kind of explaining all the principles of on-farm experimentation and how it can transform global agriculture. We are putting out every month a newsletter on the topic of on-farm experimentation via the International Society of Precision Ag. And we are also putting together a new network called the GoFen, the Global On-Farm Experimentation Network, so that we can all share tools, knowledge, develop the science, and organize. It's a little bit like a society. So Mirti and I are kind of leading this initiative. So thank you very much for your attention. We have 5 minutes for questions. David, I saw David first.
I'm wondering about the balance in the drivers behind on-farm experimentation. So, as an example, Pivot Bio is advertising on country radio stations every 5 minutes, but maybe Harold can't afford an advertisement every 5 minutes, so they'll
Something else, yeah.
Or, internationally, like JICA was always pushing effective microorganism as part of their development mandate, but maybe conventional extensionists didn't have that option that much.
Yeah.
So if the driver for on-farm experimentation is driven by a commercial entity to the disfavor of a research generated
Yes.
idea, how do you address that?
This is a great question. Okay, so we went with the pivot bio experiment. I must say foolishly now, after the fact, by kind of thinking that okay, I like the idea that nitrogen comes from a bacteria rather than coming from natural gas. So that was kind of okay. So this could be a sustainable thing because I mean we can pick and choose the experiments that we want to support. So that was kind of okay with the principles behind the farmers that I have. Okay, so then I felt like okay, could be fairly simple. It's kind of you apply it, treatment versus control. So that will make for kind of a simple learning experience as compared to maybe working more with cover crops or no-till where you can have like a lot of diversity between the control and the treatment. So we wanted to go with something simple. But you are right that we cannot just respond to like everything that is going on. So one thing, so the solution or maybe the way to work with this is to rather than taking everything that is coming our way, however it is to kind of be more purpose oriented for what we choose. So one thing that I'm thinking to do is when we do those experiment card, we may have topics, start with topics and topics that are related to actually the science that we know work and that we want to kind of push for sustainable lines. But that's important. Harold and then David.
So two quick questions. I hope that experiment that involved the end probes was thrown out because that, I mean, I get your point that, that's how the farmer wants to do it, but you got to throw out data. That's because head probes always underperform. Yes. But the other question that I have is did you, when you say pivot bio work, like in 24% of the cases, what does that mean that it worked? Did it economically work? Because you're charging quite a bit.
Yeah.
For
okay.
For
yes.
product.
Yes. Okay.
Did it actually give an economic advantage? And have you then made sort of an aggregate analysis? If it only works in 1 out of 4 cases, and you pay what was it, $20 or something like that per acre, like how does it pencil out? Yes.
Okay. This is a good point. I mean, how we determine that it worked is that with increased yield, you were in the response curve of nitrogen and the organism was present. That's what we could deal with. But you're right that we don't know if it was economically viable. We have yet to kind of dig into the data to extract all the information. And you're right that some fields we could not work with some experimental sites. So what I showed at the end was just 16 fields out of the 23 because some that are just not good enough. And actually 16 is not much to try to look for trends and patterns.
Much better than 0.
Yeah, better than 0, but it's like the idea is to find tools so that we can kind of scale because the power really comes when you have numbers.
My question is how you get the confidence that you had there. You have your interpretation tree, and each one you had a little, confidence.
Yes.
How the heck? Because I think statistics are the really difficult
Yes.
part.
Yes.
How did you calculate it?
Yeah, so we start from the premise that farmers they are used to look at their yield and decide something. Okay? But in this case, you have the data in front of you. So we did not do stats because we cannot really do stats. So what we did is that you just look at the data and you decide. So that's the farmers themselves deciding if they find that this is convincing or not. Because in the end, the conclusion will serve them. I mean, because you see, the idea.
Going back to pre-Fisher, though, I mean, this is 1924.
Yes. Yes,
a pile of potatoes and the other pile of potatoes.
yes, but in this
Don't we
case,
at a certain point want statistics that
Okay.
we know are that we're really seeing
yes,
something that's true, not just somebody's opinion?
yes. So in this case, we were looking at yield. Pretty sure we're looking at yield. And this is not, I want to work with you on this. Okay, so what I think we can solve this when you cannot conduct statistics is that with the data, you can have multiple signals. I kind of touched a little bit on this. And you will never be able to have like a 95% certainty about your conclusion. What you will be able is to have something that will hint you for the subsequent seasons to make a decision, to move on, to learn something from your experiment. And what I think is that if you have maybe 2, 3, 4, 5 signals, and the more independent those signals are, if they all point in the same direction, then that strengthens the conclusion. If they are in different direction, then it weakens the conclusion. So it's a little bit of a paradigm shift. Because we have to work with the data that exists.
This has been a production of Cornell University, on the web at cornell.edu.